To talk about implicit differentiation, I want to start us off with this parabola. All right. So if I have y equals x squared, if I can get it. Okay. Y equals x squared. And suppose I want to find the derivative of this at x equals 2. Well, let's just see what that looks like, because derivative is what? Slope. So this is y equals x squared. And if I want to find the derivative at x equals 2, well, one way to think about that is if this is x equals 2, then I go up and that's the point on the graph, and I'm like, okay, that's the slope over there, right? That's what I want to find. And algebraically, y prime is 2x. So, dy dx evaluated at x equals 2, that's 4. Okay, do you see how it was, kind of straightforward? I went to where x equals 2, I found the graph, and I took the derivative there. But now, take a look at this function here. Okay, x squared plus y squared equals 9. This is the equation of a circle with a radius of 3. Okay, so now, suppose I told you find the slope at x equals 2. Well, x equals 2 is here. You go here and you're like, oh, well, wait. There is a point on the graph above and below. So when you tell me find the slope at x equals 2, which slope is it that you want me to find? Now, it's not as straightforward, right? Because whereas here it only depended on the x, here it depends on the x and the y, because if I go to here, this y value, then I have a certain slope. But if I go to this y value, then I have a different slope. One is a negative slope, one is a positive slope, right? Huh? Well, they may or may not be. For another function, it might not, or for another relation, it might not be, right? The point being that the derivative depends on both the x and the y. Okay, so if I told you find the derivative at x equals 2, I also have to give you the y value, right? And I have to tell you, okay, find the derivative at x equals 2 comma root 5, let's say. All right, okay, what we call this, okay, the way we find the derivative in a case like this is called implicit differentiation. And let's talk about what that name means. If I just have y equals x squared, I have y explicitly written in terms of x, right? Y can be expressed in terms of x explicitly. But here, everything cannot be defined just in terms of x. It's implicitly, x and y included, right? So the way in which we're going to do this is this. We say we treat y as a differentiable function of x, and we have to differentiate both sides of the equation with respect to x. Okay, what does that mean? So to take a derivative of that function above, we have to do d dx of x squared plus y squared is equal to d dx of 9. Right, so you see the blue was our original function, and so what I have to do now is take the derivative of both sides of that equation. Okay, when I do that, when I distribute this, sort of, I get d dx of x squared plus d dx of y squared is equal to d dx of 9. Now, here's the biggie. The first one, d dx of x squared. So what would that give you? It's nothing new. What would that give you? 2x. Good. Notice it's the derivative of x squared with respect to x. Do you see how those are the same variable? Here, I want to find d dx of y squared with respect to x. And that is a problem. We kind of have to do something different with it. It's like we're going to do the chain rule, okay? So here's what we're going to do. How do you take a derivative of y squared? It'll be 2y times, remember, pretend this is a chain rule problem. So the outer function is the square. We took that, right? We brought it down. Now it's y to the 1. Now what would the inside function be? It would be that y. So times the derivative of the y times dy dx. Okay? So pretend I had this. Pretend I had this, sine of x squared, and I had to take a derivative of this. Okay? First I would do the 2. 2 sine of x times the derivative of the inside, cosine of x. Same thing, d dx of y squared. First take the derivative here, 2y times the derivative of the inside, dy dx. Okay? You just write dy dx because you can also do y prime, but dy dx, nothing else, because we don't know, like, you know, it can't be a 1 and we don't know what it is. You just write dy dx. Just go with it for the time being. And then here, d dx of a constant, that's just 0. Okay, so what we just did here is we treat y as the inside function. Okay, once you do that, remember the whole point was to solve for dy dx, right? The whole point was to get a derivative. Now we're going to solve this for dy dx, and we're going to do that using algebra. Okay, so what we have here is 2x plus 2y dy dx equals 0. Divide everything by 2, so x plus y dy dx is equal to 0. Move the x over to the other side. Y dy dx is negative x. Divide by y, so dy dx is negative x over y. Okay? And now that is the slope at any point. Okay? All right. So it's new, but we can do this. So let's do it again. Find dy dx if y squared equals x. I want us to kind of graph this first, just to see what we're looking at, just to get like our heads wrapped around it. This is y squared equals x versus x equals y squared. I'm sorry, versus y equals x squared. So it's a sideways parabola. It looks like this. So when x is 0, y is 0. When x is, so how do we solve that? How do we graph that? If you solve it for y, y is plus or minus root x, right? If you take a square root of both sides, y is plus or minus root x. So when x is 1, y is 1. When x is 4, y is 2. And here it's the negatives of that. Oops. Okay. All right. So that's how it looks. So now, I want to take a derivative here, and I want to find the slope at the point 4, 2 and 4, negative 2. All right? So, do you see how this is an implicitly defined function? We have to use implicit differentiation. So what we're going to do is, I have y squared equals x. I'm going to find dy dx of both. Okay? So, you want me to tell you the practical way of doing this? this is a y, right, with respect to x. Just take a derivative of y squared. It's 2y. But because it's the y, tack on that label dy dx. Okay? Equals to dy dx, ddx of x is 1. So now dy dx is 1 over 2y. Okay? That's the derivative. So now I'm first asked to find the derivative at 4, 2. So here's how I do that. Dy dx evaluated at 4, 2 is equal to 1 over 2 times, insert the y value, 2, 1/4. Dy dx evaluated at 4, -2, 1 over 2, -2, -1 over 4. Okay? And you can see that there is a positive and a negative slope. And as Tal had mentioned earlier, this one too, like the one before, it's going to have the same value, just negative, right? Because they're symmetric around the x-axis. Okay, so here we go. Another one. This is a very, very common problem for implicit differentiation. It'll show up all the time on your assessments, right? Like the circle. So let's go. We have to find the derivative of this on both sides. So what we're going to do is ddx, x squared plus y squared, equal to ddx of 25. Okay, so here, the derivative of x squared is 2x plus. The derivative of y squared is 2y, but since it's a y, what do? Dy dx. And that equals to the derivative of a constant, which is 0. Very common mistake, a student will just copy over that 25 there. Yeah. So it's d dx of something, and if it's d dx of y, then it's dy dx.
Like in general, what's the difference?
So here it's d dx, right? So it's basically what you're doing is it's d dx of x squared. That means the derivative of something. D dx of y squared, right? The derivative of y squared. Now, if you wanted to write the derivative of y, that's something that occurs so commonly that we just write it dy dx. Okay? Yeah. All right. So now you can divide the 2's so they go away. So bring the x over to the other side. Dy dx is equal to negative x over y.
So if we just get these questions that like slope of a circle, like we know that it's always going to be the slope.
Right, but you have to show the work. So dy dx is equal, dy dx evaluated at 3, -4. Okay, see this one, it's negative. It calls for the x value 3 over the y value, so that's 3/4. Okay? Negative x over y. Okay. Now, show that the slope is defined at every point on this graph. So basically, we have to find the slope and just show that it's always defined. That's it. So let's start by finding the slope. Okay, so I need to find the derivative of both sides. So d dx of 2y, d dx of x squared plus sine y. That's a good problem. Super exciting. I went and searched for my old calculus book. It was in my mom's garage. I found my old calculus book, and now I have like a whole new set of calculus problems. So you'll see some of them on your quiz. And it's exciting. Okay, so here, the derivative of 2y is 2. But since it's a y, d dx of y, which is dy dx, equals, okay, I need the derivative of x squared, 2x, plus the derivative of sine y. Well, the derivative of sine is cosine, but because it's a y, I also have to do dy dx. You see the pattern? Yeah? And now we need to solve for dy dx. Yes?
I'm confused why you would do the dy dx for the 2y if it would just be 2.
It would have been, if it was 2x, it would just have been 2. But since it's d dx of y, you have to do the dy dx. Okay, now we have to solve for dy dx. So whatever term has a dy dx, we have to bring it to the same side. So it's 2 dy dx minus cosine y dy dx is equal to 2x. Okay, I brought the red term here. Now, can I factor out a dy dx? I mean, I can, that's not a trick question. I factor out a dy dx, so I have 2 minus cosine y equal to 2x. And so now, dy dx is equal to, I divide by this parenthesis, 2x over 2 minus cosine y. Okay? We don't cancel out the 2's. They're fine. Okay? Now, the point of the story here was to show that the slope is defined at every point. Okay? Is it defined everywhere? So, do we have a problem with the numerator? What's the domain of the numerator? All real numbers. So, domain of 2x is all real numbers. What about the denominator? Is there a possibility that you can plug in a value for y and it makes that denominator 0? Yeah. Okay, so this is cosine of y. What's the highest value cosine of a number can have? 1, and the lowest is -1. So this is going to oscillate between 1 and -1. So it could be 1, half, 0, -1. Regardless, it's always going to be 2 minus that number, so there is no way to make that a 0. Right? Let me tell you this way. The only way to make the denominator 0 is if cosine y was equal to 2.
Yeah.
Is there any way to make cosine y equal to 2? No. There is not. So that's defined. Okay? So domain of 2 minus cosine y is also -infinity, so there is no way that that function can be undefined. You see the totally like out of the box type of question here, right? We're no longer in like pre-calc, right? We're not in Kansas anymore, right? Okay, so the process then is we differentiate both sides with respect to x, collect the terms with dy dx, factor out the dy dx, and then solve for dy dx. Okay? And of course, what would any problem be if not, to find the tangent and the normal line of the tangent line? Okay? So let's do this. Oh, look, we have an ellipse this time. Okay? Look at this problem. We have an x squared minus xy. That's going to be a what rule? Product rule. Yeah. Yeah, okay, so here's what's going to happen here. We're going to take the derivative of each side, of each term, d dx of x squared minus d dx of xy plus d dx of y squared equals d dx of 7.
Why sometimes you do ddx and then in parentheses the entire thing, and then sometimes you differentiate, like you do them individually?
Oh, so this one, oh,
Like,
technically I should have written ddx of this whole thing. I just skipped that step. Yeah. Okay. So when we get really good at this, you don't even have to write this step. You could immediately go to the next step that we're going to do, okay? So the derivative of x squared, that's just 2x. Okay, now minus this one. This one, we have to do it separately and then come back. We need the derivative of xy. That's a product rule. So u is going to be x. V is going to be y. So u prime is 1. V prime dy dx. Okay? Now, there is a minus here, so I need parentheses. X dy dx plus y. Okay, so that was just that term. Now, happily moving along. D dx of y squared. What do we get? What do we get? Oh, look at you guys. Equal to? Fabulous. Okay, let's distribute that negative. 2x minus x dy dx minus y plus 2y dy dx. I could do this all day. I am going to be doing this all day today. Oh my God, it's the first thing and the last thing I teach today. Oh no. Yes, it's the first thing and the last thing I teach today. What a nice set of bookends for me. That's awesome. Okay, so we're going to collect the dy dx's on one side, so take everything else to the other side. So it's going to be, okay, so do you guys mind if I take the dy dx to the other side just because of the negatives? It really doesn't matter, but the negatives are going to look so much prettier that way. So I'm going to leave 2x minus y here, and then take negative x over there, so it'll become positive x dy dx, negative 2y dy dx. Okay? So this is 2x minus y equal to, factor out a dy dx, and you get x minus 2y. And then dy dx, that's not a tongue twister at all. 2x minus y over x minus 2y. Okay? How does that sound? Okay. I want the tangent and the normal at this point. So I need a slope and a point. Well, I have a point. Now I need a slope. That's my expression of the slope. So what we're going to do is we're going to evaluate dy dx at negative 1, 2. And that's going to be 2 times x is negative 1 minus 2 over negative 1 minus 2 times 2. My math senses are telling me that's 4 over 5. Yeah? And then tangent. Okay. So let's find the tangent line. Okay, so it's going to be y minus the y value, which is how much? Equal to the derivative, which is 4 over 5, x plus 1. And then the normal, y minus 2 equal to negative 5 over 4, x plus 1. Whew. That's like a marathon. Right? It's, I mean, you know. All right. Okay, let's move on. Derivatives of higher order, because it's like, remember, which one was it? There was like a potato chip ad. Was it Ruffles? They'd be like, you can't stop at one. You can't just stop at one. Or was it Pringles? Which one? Well, whatever the case may be. When you're taking derivatives, you can't just stop at the first one. I'm going to take a trip here. Just a little difference in point of view. Oh, okay. It's like a different zip code over here. All right. So let's do this one. Derivatives of higher order. What if you have to do this to find the second derivative? Oh, okay. Well, let's see. Notice how there's like a whole page left here? Yeah, okay. So it's not going to take that much. Look, it's not going to take that much. Okay. So okay. So all right. So look at this. Y squared plus 2y equals 2x plus 1. We're going to use implicit differentiation. So let's do this. Okay. So d dx of both sides, y squared plus 2y equals d dx of 2x plus 1. Okay. Derivative of this side. So 2y dy dx plus derivative of 2y would have just been 2, but now it's dy dx. 2 dy dx equal to, the derivative of this is just 2 plus 0, yeah? Okay. Now, oh look, there are 2's everywhere, so we could just cancel out all the 2's, and I get y dy dx plus dy dx is equal to 1, not 0. Careful there. Okay, factoring out a dy dx, I get, whoops, parentheses, y plus 1 is equal to 1. So what's dy dx equal to? Yep, 1 over y plus 1. Great. Now let's do d squared y dx squared, the second derivative. Okay? So here's what I have. dy dx is equal to 1 over y plus 1. I left some room there after the equal sign. Because what I want to do now is take a derivative of both sides of this. Okay? So the purple is what I had down here. Now with the red, I want to take a derivative of both sides of that, because that will give me d dx of dy dx. That's d squared y dx squared. That means the second derivative equal to. Well, now how am I going to take a derivative of that one? Tell me, what's in your toolbox here? What do you guys think? No, it's the notation is d squared y over dx squared. The d gets the square on top, the x gets the square on the bottom. Because look, because each time you add a d dx, so d dx of y, and then you add another d dx. So what happens? The dx is added twice. Yeah, the dx is added twice, and the d is added twice.
It's not a d and an x.
It's exactly. It's a change in blah over. The dx is a delta x. Okay? Okay. So we can do chain rule here. I'm yelling because I'm so excited. All right, I'm going to take it down a few notches. We can do chain rule here. But what else can we do? Can we also write this as y plus 1 to the negative 1? Yes, we can, and we shall. And so now we take a derivative of that, and it's negative y plus 1 to the negative 2 times the derivative of the inside is dy dx. Yeah? Squared y dx squared is equal to, look at this. This is negative 1 over y plus 1 squared, right? Yeah? Okay, but what is this? dy dx, we can't leave that like that. What is dy dx, though? We just found it. That. So now you have to substitute in there. And it becomes times 1 over y plus 1. I know. So now, you say that now, exactly. You took the words right out of my mouth. This is negative 1 over y plus 1 cubed.
Is that a cool?
Rational powers of x, right? Taking a derivative of rational powers of x with rational powers of x. So it's the same process. We've already been working on this. These are not implicit differentiation problems, right? The reason why you know that is each of them is solved for y. This is an explicit function of y, right? This is a function of y explicitly in x. So it's just, like yesterday's derivatives, okay? All right, so y prime here, the negative half will come down. So it's 4 times negative half, x to the minus half minus 1, right? So it's negative 2, x to the negative 3 over 2. But of course, we write that as negative 2 over x to the 3 over 2. Okay? Yes. Or you can do this. Either way is fine. Okay? Either way is fine. I'll put an or here so you guys know. Okay, here. That's a product rule. But you know what? Rather than do that one, I want to do C and D. Okay, C. Okay, so look. Chain rule, right? So y prime is 3 times. First, this will move down. So we have 3 times negative 1 over 3. 2x to the negative 1 half plus 1 to the power of what? Negative 4 over 3. Okay, times the derivative of the inside. What's the derivative of the inside? 2 times negative half x to the negative 3 over 2 plus 0. Okay, the beautiful thing is these go away and these go away, and each had their own negative, even those go away. So we're left with 2x to the negative 1 half plus 1 to the negative 4 thirds, x to the negative 3 over 2. Okay, but I can't leave it that way. So everything has a negative exponent and everything's going to come down, right? So it's going to be 1 over. Okay, look at that first parenthesis. It's 2 over root x, right? Because it's x to the negative half plus 1, x to the 3 over 2. Oh, wait, this is to the power of 4 thirds. Okay? Nope. Okay.
In the parentheses, it's only one thing to take the derivative. It's not like two separate.
Yeah.
Then also, when it's like a fraction, if you're keeping it 4 over 3, could you do like your root?
You could do cube root of, yeah, blah to the power of 4.
Okay.
Yeah.
If it's just like a whole, like if it was negative 2, then you just keep it just.
Okay, look at this next one. Our first instinct would be quotient rule, right? No, yes, product rule. So my first instinct would have been quotient rule. But my experience has taught me to do product rule instead. And the way I can do that is I could do x times x squared plus 1 to the negative 1 half. Okay? Yeah. Yeah? Okay, so now u is x. V is x squared plus 1 to the negative half. Okay, u prime, 1. V prime, negative 1/2, x squared plus 1, negative 3 over 2, times 2x. Okay, these go away. So let's see what we've got. Y prime is u times v, so x times all this, okay? So you see how there is another x here? So it's going to be negative x squared plus 1 to the negative 3 over 2. Because it's u is x, and then there is also an x in the v prime. Okay, plus this way I get x squared plus 1 to the negative 1/2. Okay. Now, do you remember I showed you guys how to factor out the smaller term with the smaller exponent? Look at this. I have x squared plus 1, x squared plus 1. I can factor out those terms, right? They have different exponents. Of the two exponents, which is the one I can factor out? The smaller number, which is negative 3 over 2. So I'm going to factor out x squared plus 1 to the negative 3 over 2. Okay, now look. When we're first learning or getting comfortable with how to do this, always think to yourself and write down that when you factor something out, it's like dividing by what you're factoring out. I want to pepper in as much of these as I can to get you guys used to it little by little, right? So here this cancels out and I only have negative x squared. Plus, here I'm dividing two powers. Go back to your algebra skills, like way back algebra 1. Two powers, same base, different exponents. You keep the same base, but you subtract the exponents. And you know what? Write that down. You're not going to lose points for writing in too much work. So just write it down, because when you're rushing, it's so easy to get the negatives wrong there. And you'll end up with a half versus a 1 versus a 2, okay? So now I have y prime is equal to x squared plus 1 to the negative 3 over 2 times negative x squared. And what's this here? Positive 3 over 2 minus half is 1. So look, these go away. So y prime is just this times 1. So 1 over x squared plus 1 to the 3 over 2. Okay?